In this video, I'm going to introduce exponents and scientific notation. Exponent rules and scientific notation. Alright, so hopefully you've seen stuff like this in the past. Okay, now let's first of all, let's talk about nomenclature. Okay, when you see a little number floating on the upper right of a number like that, these little numbers, these are called exponents. Okay, and the big number that the exponent is hovering above, okay, so the 2 and the 5, those are called bases. That's the bases of, you have exponents floating, hovering above bases, okay? And so there's the nomenclature, and this really is nothing more profound than an abbreviation. Okay, if you understand multiplication, you understand exponents. What's happened was, at some point in history, somebody got tired of writing out a lot of multiplication. So they said, instead of writing 2 times 2 times 2, whenever I have a lot of repetition like that, let's float a little number, and that represents the how many of the base I'm multiplying together. So 2 times 2 to the 3, 2 with an exponent of 3, that means you multiply 2 times 2 times 2, and so that gives 8. Okay? Think of exponents as repetitive multiplication. Just like multiplication is repetitive addition. Okay? And then for the 5 squared, that's the same as 5 times itself. You have 2 of them, and so that gives 25. Okay? Now, some exponents are some bases are much nicer to work with than others. Okay? You probably could have figured out these two problems, these green problems, on your own, given a few seconds. But what about, these are even nicer than that. What if I had a base of 10? Okay, if you work out a few problems with a base of 10, you'll notice that the answers come out very simple and nice. Okay, you should be able to see a pattern. Okay, the pattern is that the number of zeros on the answer is equal to the exponent. Okay, and this is also true. We will talk in a different video in more detail about negative exponents, but I can go ahead and show you the pattern now for just a base 10. Okay, and so there's a pattern here. What's going on with the negative exponents is that the answer has one less zero to the right of the decimal than the absolute value of the exponent. Okay, that's one way to think about it. Okay, another way to think about it is that you start with a 1. I'm giving you 2 alternate ways to memorize the negative exponent answers. Okay, imagine that you start with a 1, and when you have 10 to the minus 1, you have to take that decimal, let's say it's 1.0, and you have to move it to the left one hop. If you do that, you'll get the 0.1. See that? Now on the 10 to the minus 2, you might remember that this way. So you say, okay, so the decimal has to take 2 hops to the left. So 1, 2, and so we'll put a 0 in between, and so that's why that one's 0.01. And then let's go to the last one. The last one means 4 hops to the right. So 1, 2, 3, 4, and then you can put a 0 for each of those little hops, and so the answer has to be 0.001. All right, pick whichever way works to help you memorize those. Now, there's lots of reasons to use exponents. One big reason, again, is it simplifies when we have a lot of repeated multiplication. Another reason is when you have really big numbers, you don't want to always be writing zeros. Like, let's say you were dealing with, millions and billions of dollars or whatever. Okay, you don't want to always be writing 6 zeros, 9 zeros. So we can use exponents to avoid all that tedious writing. Okay, this gets into, scientists use this a lot. So the using exponents to abbreviate super big or super small numbers is referred to as scientific notation. All right. Let's say that I had the 1,234,000. Okay, 1,234,000. Okay, so you can write that as the small number 1.234, and if you multiply that by 10 to the 6, 10 to the 6 by the way is a million, so 1.234 times a million will give you the original number. Okay, and so the right side is scientific notation. Okay, let's do a really small number. Let's say that I had something like 0.00000035. You can see how annoying it would be to write that all day. Okay, so what I'm going to do is we're going to write it as 3.5 times 10 to the minus something. Okay, and that's going to be a lot nicer to write over and over again. Okay, and the way that we figured out was the similar trick to what I talked about before, the number of hops to get from move the decimal around. Okay, so we want we want to know how many hops there are between where the decimal is on the left now and where it is at 3.5. So 1, 2, 3, 4, 5, 6. Okay, so that means it's going to be 10 to the minus 6. Okay, if you want to check that, again, I always encourage you to check anything I say in the video. Go ahead and on your calculator try putting 3.5 times 10 to the minus 6. You'll see that it gives you the decimal on the left with 5 zeros to the right of the decimal. Okay, and if there's another way you can work that out to convince yourself, by all means go ahead and do that. All right, so this is scientific notation. Let me give you a few practice problems and then I'll finish with adding and subtracting numbers in scientific notation. So what about if we had, let's do a big and small number. Let's do that. What about 6,700? Can you write that in similar to how I did it on the right side? And also 0.004. Can you write that with some kind of exponent? Okay, so I'll go ahead and work it out now. 6,700, you can work it out and see that that one is equal to this, and the bottom one is equal to this. And a sneaky way to figure out what the exponent is again, use my little hop trick. So 6.7, right now the decimal is after the second zero. So can you see that there's 3 hops between the two places where we're starting and ending the decimal? That's how I knew it was 3. Okay, for the last one, again, same thing, there's 3 hops. Okay, now notice that different directions make the exponent to be positive or negative. The really small numbers are going to have negative exponents. The big numbers like 6,700 are going to have positive exponents. Now, you may, I don't know if you worked it out before I gave you the answer, you may have said that the answer for you may have said that was 67 times 10 to the 2. Okay, or you even could have said 670 times 10 to the 1. All right, all of those are equal. So then the question is, which one is correct? Okay, the convention, this is just a convention, in order that we all mean the same thing when we say scientific notation, we want people to always give an answer where the number in front, that number is between 1 and 10. If you look, I always had a number that was between 1 and 10. Okay, now these other answers are not correct. Okay, It's just that we would prefer that you use the number on the left to be between 1 and 10. All right. Scientific notation is defined with the number between 1 and 10, not a bigger or smaller number. Okay, and then once you've got scientific notation down, you can add and subtract big numbers pretty easily. Let me go to a new whiteboard and show you what I mean by that. So if I had like 1.2 times 10 to the 15, that's a huge number, plus 3 times 10 to the 15, all I have to do is focus on the piece in front. Okay, so 1.2, add those pieces together. So 1.2 and 3, that adds to 4.2. See that? And that's it. And then subtraction is similar. Okay, this time let's do a really small number. Suppose I had 7.8 times 10 to the minus 403 minus 1.2 times 10 to the minus 403. Again, same idea. Just focus, ignore the exponent base stuff and just focus on the number in front. So 7.8 minus 1.2 gives 6.6, and then the base and exponent just come along for the ride, and there you go. All right. Now, everything is well and good as long as both parts have the same exponent. Okay? If they don't, we've got to do some adjusting. Okay? So, let me show you what I mean by that. So, suppose I wanted to add 6,000 to 600. Okay, that would give 6,600 clearly. But let me do it in scientific notation. So 6,000 is equal to that. 600 is equal to that. Okay. Now, the exponents are not the same, are they? Okay, so you can't just do 6 plus 6, so the answer is 12 times something. What you have to do is you need to adjust one or both so that they do have the same exponent. Okay. What if we made for the we can do it both ways. What if either way, what if we made on the second scientific notation number, what if we made, whoops, remove that equal. What if we made the 6 smaller, so we made it into a 0.6, but in order to do that, we're going to compensate by making the exponent bigger. Okay? If we did that, now we can go ahead and add them together because the exponents are the same. Okay? And these, they're the same, they're equal. Okay, so everything's good. Now you also could have changed them both to an exponent of 2. For the first one, 6 times 10 to the 3. Let's make that. Let's make the 60. Let's make the 6 into a 60. Then let's make it bigger. But to compensate, let's make the exponent smaller. And okay, now you can add the 60 and the 6, so 66 times 10 to the 2. Now that's not correct scientific notation, but it's still an equivalent, it's still an equal number. Okay, and then if you wanted to, if you did this, you could go ahead and adjust. You could make the 66 smaller and then compensate by making the exponent bigger. Okay, so you can get comfortable with adjusting the exponent and adjusting the number in front to compensate. Okay?